Thank you, Pius, for getting the doors closed bit by bit. Welcome to all of you students. Good to see you. I hope everyone's comfortable. Some of you, did anyone just have a Bio 120 lecture just before this? Look at that, yeah. It's probably just sit in the same seat, right? It's a 10-minute break, and now you're on to physics. And there's a lot fewer people in physics. So. You got to be into it. Somebody said to me once, my thesis advisor told me when I wanted to study astronomy for my PhD, he said, you know, there's no pot of gold at the end of this rainbow. I don't know what he meant by that, but I was like, but I want to do astronomy. Okay, we're continuing on with chapter 2 today, so I think I might just dive right into it. Do you remember I kind of ran out of time last time, but it was pretty straightforward. But I kind of want to go through this concept of making a position versus time graph somewhat carefully and just kind of go through the steps. And this may seem a little pedantic to you, but I think it's important. And you can sort of see the steps on these left-hand graphs there. But basically it's this. Imagine there is some motion, and let's just take the very simplest thing, is I hold my hand up next to a ruler and move a ball 20 centimeters over 10 seconds. So that's what I'm trying to describe. It's a process that I'm trying to describe. Okay, so I could give a before and after, right? That's one way, and I could maybe have a stopwatch or something in which I could say those times. Click, beginning, and then wait till the 10 seconds goes by. I've moved it a little bit, very slowly, obviously. 10 seconds is a long time, 9 and 10, click. And it's in a different position. So you've got before and after. But if you really wanted to describe all the motion in between, you could, for example, just make a table, okay? In which you've got, for every second of time on the stopwatch, you have a corresponding position along the ruler. In this case, the ruler is going up or something, but the ruler could be sideways, or you could imagine describing lots of different kinds of motion this way. And then once you have a table of pairs of numbers here, then you can make a graph. And that's all this is. So, and you have to choose which, like your left-right axis, your x-axis, and your up-down axis, your y-axis, which you're going to plot on which. Neither of these is y. You're actually plotting time on one of the axes and position on the other axis, so it doesn't matter where you put them. Traditionally, I think what we tend to do is put the time on the left-right axis, just it's convenient. And then the up-down axis, we put position. And it doesn't matter if it's actually moving up or down, it could be moving sideways, but we plot it on the up-down axis because just time was over there on the horizontal axis, okay? And it looks like this. Again, I'm going through this kind of very slowly and pedantically, but there's a bunch of dots, and you can see these dots match up to positions or to pairs of numbers. There's a 0, 0, well, there's 0, 0. Then there's 1, 2. So time, 1 second, 2 centimeters is right there. And then like that's 5 seconds. At 5 seconds, the thing is up at 10 centimeters. And then what you can do from there is once you have a line of dots, you can connect the dots with a trend line. And again, seems pretty simple, but it's a bit profound, actually. What you are saying by drawing this line is not only do you know the position of this dot at 10 different, 11 different instants of time that you've measured, but you can somehow infer from that exactly where it is at an infinite number of little times in between all of your measurements, because I guess we make this assumption that things move. If you move from A to B, you have to pass through all of the infinite number of little points between A and B, but I won't get too philosophical. You just draw a line. And that's now called a position versus time graph. It's pretty. Just wanted to kind of go through that carefully. And now do you want to do this? Some of you, maybe all of you, have already done this question, but I want to do it again. In class. So right now, on learning catalytics, if you go on there, there should only be one session. And if you are here right now, it's this number up there that you see. And if you're on the video, then what's going to happen, so I'm speaking to future video people, like in about 3 hours from now when I post the video, this will be done, and everyone here will have received their marks, but you will be able to join the async learning catalytics and see the same questions, just kind of follow along with it. Please discuss, maybe, what you think. One of these is just not possible, and the other 3 are fine, actually. See if you can sort of explain to your neighbor how that's possible. So just as a warning, at some point, I'm going to be asking people to stand up. So I don't know if there's a place to put your laptop when you stand up. Just a brief stretch, but it's not happening quite yet. Whoop. Okay, phone. I'm going to stop this one. So if this is a time to click in, I have 244 responses. Going once. Oop. Now I have 469 responses. Wow. Going twice. Let's do stop delivery. If I do laptop 2, send to all, you can see that 94% of you have voted for D. So this is the one that I kind of wanted. So basically, Mia is cycling at a constant velocity, meaning that there should be some constant slope. And depending on if she's cycling towards the negative x direction or the positive x direction, you could have an A or C, could be, A or B, it could be there, she's going in the positive x direction. C, she's going in the negative x direction, it's just the other way, at a steady speed. And maybe the difference between A and B might be that she started not at x equals 0 or at some other position. So there's all sorts of things. The one that doesn't work is D, because a horizontal line on a position versus time graph means that at every instant of time you're at the same position. And that means that you're not moving at all. So that's not allowed. And remember that these are position versus time graphs. Don't mix them up with, if you're reading ahead, there's all these velocity versus time graphs. And in that case, if these had been V versus T, then D would have been the one that is possible. Sorry, yeah, not correct answer, but the correct graph. Maybe show what you should say. Let's get this right. The correct graph. Well, the only correct graph would be D in that case. Not correct answer. Correct answer was D. Make sense? Okay, done that. And then, so again, back to position versus time graphs, very simple. The steeper the slope, the faster it's going. This is a little bit like the distance between the dots or something, or distance between the bean bags is on the vertical axis there for a certain amount of time. So if you're going farther for the same amount of time, then that's a steeper slope, going faster. Whereas if you, remember the distance is up and down, if you're not going very far in the rise for a longer run of time, that means you're traveling slower, and zero slope means it's not moving. So the slope is going to be related to the velocity. Okay. Let's see what we're doing for time here. We're going to get into vectors, I think, next. Doing great. All right. So the next thing we're going to do on learning catalytics, which would be a lot of fun, and I hope it works, is try to draw vectors. And it's about vector mass. So basically, a vector is a quantity that is fully described by, wrong. A scalar. A scalar is a quantity that's fully described by one number. And examples of that are mass, temperature, or volume. As opposed to a vector. A vector is different than a scalar. A scalar you can plug into your calculator. That's sort of what you're used to, like 3, or -1. These are all scalars. 0. Vectors, you can't just type them into your calculator. They have two things, a magnitude and a direction. It always takes at least two numbers to really specify, or at least two pieces of information to really specify a vector. And the geometric representation of a vector is you draw an arrow on your page, or with your finger on your laptop in this case. Okay. We label vectors by drawing, sometimes you can label, I guess, a scalar as a letter, like V, and then the vector, we tend to put a little arrow on the top of it, just to remind us that it's different. So this is a vector, this is a scalar. And the way I say it here, actually, is that this, let's go to blue. This thing here, V, with an arrow on the top, is called the velocity. That's what the V stands for. And then V without the arrow on the top, it's the magnitude of the velocity, but sometimes V is called the speed. It's just a number. It's a scalar which represents the length of the vector, even though it doesn't start with V. Okay. Anyway, we'll be doing a lot of this using vectors, but vector addition, vector math or something is not the same as regular math. You have to take into account the direction. So, example, if you have E pointing up and D pointing on the diagonal, it's convenient sometimes to draw the vectors with their tails together. So each vector has a head and a tail. The head is with the arrow. The tail is without the arrow. And then to evaluate the sum, what you do is you connect the tail of the second vector to the head of the first vector, and then draw a new vector that goes from the tail of the first to the head of the second. And that's what's done in the tip-to-tail rule. Alternatively, some people use what's called the parallelogram rule, which is that you just leave them with their tails connected and then make a parallelogram, and the diagonal across that parallelogram is the sum, vector sum. Same answer both ways. So now we're going to see if we can deliver question 2 without too much pain. So I don't know if this is showing up on your little screen now, but I want you to estimate with your thingy or something the sum of U plus V. Maybe a minute. Take a look at what's going on the floor. Feel free to look over your neighbor's shoulder if you want to discuss this. Remember, I don't know how these are graded, but it's always 80% just participation. Right? So, whoop. Can you maybe give you another 10 seconds just to try to give an estimate for this in roughly the right direction? Sometimes I think the parallelogram rule might be the easiest. Well, this is so cool. It's sort of giving a... All right, I'm going to stop it because then we're going to do a minus one. Do you want us going once? Going twice? Let's do stop and laptop 2. I can show you sort of what I've see. It somehow marked 95% of you as correct. Even though it looks like you're all kind of in exactly the right direction, maybe 5% of you didn't drag it exactly the right distance. So hopefully that's not, but you got the right idea, right? Which is, let's go back to laptop. You kind of, you want to go, I would just do tip to tail. So I would say, starting from here, this is up and to the right, up 2 and to the right 1. So this is the end. So you kind of want to draw an arrow that ends at 4 and -2. And this is u plus v. And then you can multiply a vector times a scalar. And this is the rule of how you do that, which is when a vector is multiplied by a scalar, the result is a vector that's parallel to the original vector, but it's scaled by that new magnitude. You multiply the magnitude by that number. Unless the scalar is negative, in which case you do that, but you reverse the direction. So we always say that the negative of a vector is the same magnitude vector, but in the opposite direction. Which actually makes sense, because if you add a scalar, like 5 plus -5, you get 0, right? Well, it's the same with vectors. If you add a vector to its negative vector, you'll get back to the origin, right, which is 0. So I like that one. So I'll try another, this is the last draw a picture question. This one is deliver. So now you want to do, now they're different vectors, but it's u minus v. And the hint here is that if you want to subtract v, it's the same as adding -v. So what I would do if I were you, if I want to do u minus v, is the first step is I would take whatever -v is, and then I just add it to u. I'll give you 1 minute to discuss that one. Think about it. I'll kind of end this. I'm going to give you 5 seconds to plug in. What is it saying here? Okay. Going once, going twice. And I'm going to stop delivery. Click. And show you what I'm seeing. So this was a little more controversial. People were kind of, it's good to know. But let me just show you what I did, or I would do, if I were you, is I would say, first step is draw out a negative v. And negative v is going to look like this. This is negative v. And then I would just take this thingy and add it tip to tail to that one. So like that. This is negative v. And then this vector right here, from 0 to, I guess, 2 and minus 2, this is v. Wait, sorry, wrong. Let's get it right. Because the u minus v is not the same as v minus u, right? I have to get it right. It's, it is u minus v, this vector. Okay? So that's vector subtraction, which is going to also be kind of important. These things come up in kinematics because velocity is going to be the change in a position vector divided by time. And the change in a position vector is the final vector minus the initial vector. So let me show you how it looks. I'll go through these slides a little quick. This is a sled that is sliding down a hill. And you can see from the motion diagram that it's kind of getting faster and faster because these are equal moments in, or equal intervals in time. But the distance keeps getting larger as time goes on because the sled is speeding up. Anyway, that's where it was. Position measurements can be made by laying out, this is actually an XY coordinate system. And then you've got something called R, where R is a vector, starts at the origin and ends up where the object is. Great. So there's sort of a motion diagram for the sled, which we've drawn on an XY coordinate system. And we said the motion is a change in the object position with time, but how do we show a change in position? Well, for example, between t equals 3 seconds and 4 seconds, we draw an arrow between the two dots of the motion diagram. And the way that looks, I always get kind of confused with the where to draw the delta. But basically, this triangle is the Greek letter delta, and it means the change in. So the way it's defined, some people put that delta R is equal to R4, the final minus the initial. So how do you remember that the delta is final minus initial? The way I remember that is I try to think of it as in the sum. So you take the initial, like R3, plus the change in R equals what it gets to. So I would just, let's do a different color here. Initial plus the change equals the final. That equation makes a little more sense to me. And if I rearrange that equation, I find this. The delta is R4 minus R3. Or RF final minus R initial or something. So that's where this vector subtraction and addition comes up in physics in chapter 2. And then the other thing is pretty easy. It's because the scalar is just the time. Okay? Whoop. Which is you measure it on a stopwatch. It's used to measure a time interval. That's an analog stopwatch, but you can have a digital one as well. And the time interval is the final time minus the initial, T2 minus T1 or something, or TF minus TI or something. And the delta, once again, represents the change in. And these ones, luckily, are both scalar quantities. So, wait, just stop that right there. That was to remind me that we're going to do the wave here. So let's do this one. So remember I said, it's now 11:35, so we're halfway through the class. So what I was thinking is that we would stand up, Now, I've just walked around and I've noticed that some of you have a laptop on your lap, and some of you have two laptops on your lap. And so, I don't know if you can put them down, but I'm going to ask you to stand up in a minute, not quite yet. First, I want to measure a distance, and then we'll measure the time, and then we'll do let's go to maybe right around here. Let's see if we can measure this out between Pius and me. Because I want to know, you know how you see the wave when you watch the Blue Jays? How fast does it go? And we're going to measure that right here. Maybe this is the only time anyone's ever measured it. I don't know. Start around. You guys are going to start, okay? So this is the start. 17.8. Let's just give it rounded off. Let's call it 18 meters. Okay. Thank you, Pius. I'll just put that down. Let's write it down. And then I got a stopwatch for which I'm going to measure the time. Now so delta x equals 18 meters. Delta t we're going to measure, and the way we're going to do this is basically you people over here are going to wait for me to go 1, 2, 3, go, and then you're going to stand up and say, whoa, and then sit back down again. So that's your job. Everybody else, what you're going to do is wait until the person beside you is standing up and saying, whoa, and then you have to stand up and say, whoa, and then sit back down again. Make sense? If you watch baseball live, sometimes this happens. And you have to put down your beer and stand up and say, whoa, and then sit back down and get your beer again. Okay. Are we up for this? Laptops need to go somewhere safe. Please try not to step on your neighbor's laptop when you're doing this. That's the main thing. And I'll measure the time, and then we'll compute the speed of the wave. So this is a science experiment. This is not supposed to be fun. Okay? And you people on the balcony, you just kind of have to follow along, okay, with the people below you, which you can't see. But you can see these folks down here, right? You're going to do it? You're going to stand up? Be ready. Laptops on the floor. Don't step on your laptops. 1, 2, 3, go! Stop! Okay, 6.25 seconds. Excellent. Nice work, everybody. So, we will do equals. Get out my calculator. It's going to be 18 meters divided by 6.25 seconds. I should probably be careful with my significant digits. You know, I don't really need all these. But I got 2.88. And so the units are going to be meters per second. So I would write, to be more honest, 3 meters per second, roughly, just because I don't really trust any of my measurements to that many significant. But it may be 2.9, something like that. You know. Anyway, so that was fun. All right, so back to physics. So yeah, this is, I'm going to go through chapter 2.4, in which she describes position, displacement, distance, and path length. And it's a little more complicated than it needs to be. These quantities describe the location and motion of an object. Okay, position is just an object's location on a coordinate system. Displacement is a vector that starts from an initial position and ends at its final position. And this is where I get mixed up. Distance is the magnitude of the displacement vector, and path length is how far the object moved as it traveled from its initial to its final position. So we're just going to draw it. Imagine, and what Pius and I did there is we laid a string or a ruler or something along the path that the object took, which in this case was, I don't know what the object was that we just measured. If you think about it, nothing moved, right? You guys just stood up and... But I saw something really cool happen, which was this wave, and I could point at it, of people going, whoa, and it moved, whatever it was, moved from there all the way over there. So we should think, what moved? Was it the energy? Was it the woe-ness? Or I don't know what moved. Something moved. I know that it moved because I could point my finger at it. and look at it. Anyways, let's not get, again, I get too philosophical in this class. So, a car backs up, moving in the negative direction towards the origin of the coordinate system at x equals 0. The car stops and then moves in a positive direction to its final position of x final. So we're going to do, actually it's going to start here. Let's draw a little car. This is about how good my diagrams get. Car, in case, you know. And then you could say that this is x sub I. This is the initial position. Okay? And what we're going to say that it does is that it goes backwards, comes to the end where this is the final position. Draw in blue here. Again, it's a car, and this is x final. So that's where position gets defined. That's positions x final and x initial. What about the displacement? So that's easy. You just do this. Oops. X initial and x final. My drawings are getting worse and worse. This is the displacement vector, d, and the distance, d, is just equal to x final minus x initial. It's not the same as the path length, because it backed up to the origin. Sometimes we say that d is the magnitude of d, with an arrow on top. And then, last one is path length L. So that is where you have to take into account where it actually traveled. So this again is x initial, and this is x final. But if you read carefully, you'll see that the car first backed up. So it went from there to the origin, and then up to the front again. So the path length L is equal to, first of all, xi, and then plus xf, because this distance right here is the xi from here to here, and this distance from 0 to out here is the x final. So if you were to lay out a ruler or something to measure that whole distance, that's what that would look like. And I'll just note here that L is not the same as the distance. It's kind of weird, actually, because L was xi plus xf, and the distance was xf minus xi. Anyway. Distance just meaning, in this case, with this textbook, it means the magnitude of the displacement vector. Okay, hopefully that is helpful. The next thing is velocity, and then we'll kind of be done. We might talk a little bit about acceleration just before we leave, but basically, velocity is the slope of position versus time graph. Slope being rise over run, which you can do. If the slope is positive, then we say the object is moving in the plus x direction. If the slope is negative, this Vx, okay, we say that the object is moving in the negative x direction, the opposite direction. So the magnitude of the slope represents the speed of the object, and the direction, and the speed and the direction together are what we call the velocity vector. So I want to do another, I think I've got another learning catalytics. This is just sort of a word question. This is a discussion question. Let me press deliver. So this is a multiple choice question which should show up on your phone right now. If the position versus time graph of an object moving in one dimension, so like along the x-axis or something, is a straight line, what does this mean? A, the object's not moving, B, the object's moving with a constant velocity, or C, the object's moving with constant acceleration. I'll give you 1 minute to discuss this. I don't know if this is the best worded question. You might be mad at me when you see the answer, but just try to pick what you think is the best answer. Doesn't matter what you answer for that 80%. Remember, going once, going twice. Let me just make sure there's somebody answered here. I have to refresh. I see 568 responses now, so people are really here. This is good. And stop. This is really, you guys are going to laugh again. So it was 49% versus 49% versus 2%. So nobody liked C, but it was a dead split between A and B. And my personal answer is B. So, so let me show you why I think that. And again, hopefully no one's brought any rotten tomatoes to throw at me or something like that. This is what I'm trying to say here. I guess A might be true if the line was straight and it was horizontal, but B, to me, is a better answer because the word straight means not curved. But actually, C is technically true as well because the acceleration is 0, and 0 is a constant. It's just a specific constant, right? So, anyway, sorry, bad question, bad prof. Okay, let's see. So what they call a trick question. There's going to be one more question for redemption here. Yeah, here it is. I hope this one's less tricky. So by velocity now, and I'm going to say this in a bit, what I mean is now the slope of the tangent. So the velocity of an object can change, and if you have a curvy line, if you want to know the velocity at a particular point on the line, like at a particular instant of time, you drop a tangent and measure the slope of the tangent, okay? So try that. Again, I'll give you a minute. Okay, what time is it? And just give me like one significant digit. I heard somebody yelling out 2.8. What's all this? Come on, guys. All right, I'll do a refresh. I have 568 responses. Going once? Going twice? You're fine. I think if you're allowed to change your answer, it's your final answer that sticks. I'll do stop delivery and laptop to send all. So there we go. That's what I like to see. This is when the professor doesn't give you an evil question. You guys are 91%, so okay. But let's go over it anyways. Meaning that what you do is drop a tangent. So it starts off, let's do it in red, shall we? I think B starts from rest, if that makes any sense. We sometimes say an object is dropped from rest, or starts from rest, and then it accelerates. Sometimes there's a slope or something. Like if it starts from rest, it might just sit there. Whoop, you stop now, you. Wow, it just goes. It started from rest, and you let it go. It goes down the hill. You can tell the building was built in 1907. Okay, it's accelerating, okay? And so that's what's happening in B, is that it's speeding up. Where do you go? Let's kick him that way. See if he goes to the ramp. You go that way. That's a frictionless puck, which is now escaped. We're going to do this again when we get to collisions. I have two of them. We're going to collide them, and we'll send it to Pius. There we go. Constant velocity. Zero friction, constant velocity. That's another Newton's law to remember. Then it speeds up, and the slope gets, so this is, at this point right around here, 2.8. Wait a minute. No. Okay, sorry. It's 3. Roughly, okay? Is where the slope of B equals the slope of A, and then it's faster. So they have the same velocity somewhere around C, is what I was going for there. All right. I gotta stop joking around. We're getting into acceleration, and I know you've been asked some dynamic study module questions about acceleration already, but I'm gonna try to define it right now, which is, okay, I wanna ask you again one of these philosophical questions. Do you think there is a difference between position and velocity? Obviously, right? Well, what I'm here to tell you is that that difference between position and velocity is exactly analogous to the difference between velocity and acceleration. Acceleration is as different from velocity as velocity is from position. And so if you kind of think, oh, high acceleration, high velocity or something in your mind, you're dead wrong. They're completely different. Velocity is that thing you kind of get, which is it's moving, and acceleration is kind of more complicated. So, but it's not too bad. Basically, it's just this. V is the slope of a tangent of x versus versus t, sorry. X versus time. So, example, if I say this time instant right there, I drop a little tangent, I do a little rise over run, a little delta x, and a delta t. I say that this v is equal to, now if it's really small, you can say dx divided by dt, but let's just use deltas, because this is an algebra-based course. And the units here, let's keep track of the units in black, units are going to be meters divided by second, okay? Meters per second. Per second. Now, okay, so this is the tricky part. I'm going to try to draw the acceleration as being the slope. So this is v now. So v would be here, and it gets to some maximum maybe around here. And then another minimum sort of around maybe here. And it goes up again. So I'm going to draw, I don't know if I'm doing this right. Let's just say that that's the slope. What I've tried to estimate there is the slope of that line plotted at every instant of time. So now I have a v versus t graph. Same thing. If I want to get a now, I just drop a tangent. So if I wanted to do it right here, drop a tangent. This is going to be delta v, because that's how much the velocity, and this is delta t. And we say that a is equal to delta v divided by delta t. It's easy. And then the units, if we want to keep track of that, are going to be actually meters per second divided by second, which equals meters per second squared. Meters per second squared. And that's basically it. So if you can understand how you go from position to velocity, then you can understand how you go from velocity to acceleration. It's the rate of change of the velocity, or the slope of a tangent of a v versus t graph. And this is going to come back again and again and again in this course. This is a really kind of important slide to get the concept of in your head. It's sort of a calculus concept, honestly. This is the derivative. V is the derivative of x, and a is the derivative of v. So last day at the end of the class, I asked, does constant velocity imply constant acceleration? Yeah, I guess. In addition, it implies zero acceleration. And zero is a constant. Then I asked, does constant acceleration imply constant velocity? The answer is no, unless that constant happens to be zero. Basically, constant acceleration means that it's constantly changing its velocity, like when that puck was going down the slope. At every instant, the velocity is getting bigger and bigger, and so the acceleration is not zero. So velocity is the time derivative of position. Acceleration is the time derivative of velocity, and by that I just mean the slope of the tangent. And the SI unit of acceleration is meters per second, also called meters per second squared. So some people call it like the speed of the speed, or how fast changes or something. It's a weird, tricky little concept, but it's going to come up when you do F equals ma, so you better have a good handle on it. And it is possible for an object to be momentarily stopped with a non-zero acceleration, believe it or not. We will get into that a little more next time. So what I want you to do is try to think of an example of an object with negative acceleration, which is speeding up. That's one. Two, think of an example of an object with a positive acceleration, which is slowing down. If you can imagine that. We're going to do these in class on Friday.